Hello and welcome to Sean White's Solar and Energy Storage Podcast. Today, our special guest is Lennart Hinrichs of TWAICE. And TWAICE is spelled kind of funky, and Lennart is also in charge of all the Americas. I guess that makes you more important than Trump. Is that correct?
Well, dangerous thing to say as a foreigner being in this country, I guess. But we are definitely doing our best to drive forward the renewable agenda here in the US and help the BESS industry to become more independent.
Great, great. And so what is it that you're doing with TWAICE? And let's just say how it is spelled. It's TWAICE with an AI in it, TWAICE, TWAICE. What are you guys up to, besides taking over the Americas?
Well, since you spelled it out and it's clear that the AI is in the name, you could say we're bringing the AI into battery energy storage systems. So what that means is really a data analytics platform that helps owners, operators of BESS systems to take full control of their data and then improve the performance, safety, and operations of their storages, meaning anything related as well to their supplier management, warranty contract monitoring, reporting, asset management, and performance engineering.
Great. Does it do anything with deciding when to charge the battery and when to export?
Yeah, so we don't look at the market optimization. So there's plenty of companies out there that do a phenomenal job in predicting demand and really making sure that you have a discharge at the right moment. Our role is really to ensure that when you want to have a discharge, the storage and the battery actually works.
Mm-hmm. Okay. So maybe you could tell us just a little bit more about what your value proposition is and how people could work with you and how it works.
So when you operate a battery energy storage system, there's a number of challenges that you're facing, mostly coming from the large amounts of battery cells that need to work in harmony, creating oftentimes so-called imbalances in the system. These can come from just the natural temperature gradient and resistance within the system, meaning some cells are a bit more charged than others, limiting the overall operation. Can also come from the millions of components that are part of a large-scale BESS that can fail. So in order to ensure that you have a smooth operation, you need to ensure that both the system is in balance, that all the components are functioning properly, and you don't get any downtime of, say, a PCS system that takes an entire battery bank offline, or weak cells in the systems that cause a larger imbalance. That means that you're removing capacity from the battery. Ultimately, you can trade less than you would like to, or ultimately also cause a safety risk. So ultimately, if you want the full nameplate capacity and power for the duration that the storage system is set up with, and I'm assuming that all our listeners here understand fully how a BESS is marketized, then you need to make sure that you have little imbalances in the system, that the system is fully calibrated when it comes to the SoC algorithms, so that the controlling entities also know how much energy do I actually have to discharge or charge at any given time, and with how much power can I do that. So how many of the PCS are currently online and how many of the racks behind these PCS are functioning properly at the moment. And what TWAICE does, because you have these billions of data points that come in from the batteries, TWAICE harmonizes all that data and provides you the actionable insights to give you a clear idea. This is exactly what I can discharge at the moment, and this is exactly the components that are currently causing me to lose energy or power in this direction.
Okay, and I think I'd like to define some of these acronyms here. And so we have BESS, and that stands for Battery Energy Storage System. PCS, Power Control System, and SoC is State of Charge, just to make sure that everybody's, most people probably know about that, but I just like to always define things like that.
Yeah, maybe just quick on the PCS, the kind of power conversion system.
Oh, and you're using PCS for power conversion system?
It's the inverter. It's bringing it from DC to AC. So.
Okay, so that's a little bit different than what I teach is PCS is power control system, and that's what it's called in the US in the National Electrical Code. So that's why it's good to always explain the different abbreviations and acronyms. So for us, we might call what you're calling a power control system. Actually, it's in the NEC, in the 2026 NEC, they're calling it an EPC, electronic power converter. And of course, you probably think of an EPC as engineering, procurement, and construction. And so there's just like so many different, people call them 3-letter acronyms, but actually if they don't spell something like BESS, if you just said BESS, then it would be an abbreviation. And an acronym is when you can kind of sound it out.
Yeah,
Yeah.
absolutely. No, thanks for that clarification. And you're absolutely right. I think just talking about the best side as a whole as well. I mean, you coming from the high voltage and then kind of have the transformers and the substation transformers to bring it down to, I mean, it's still, I think, depending on the definition, but it's the lower voltage of the batteries. And then you have the inverters or PCS system converting it to the DC power that the batteries run on, and then you have the different. So if you look at a BESS, I mean, just to get the nomenclature right here as well, the smallest unit, I mean, if we're not going into the chemistry really, is the cells. Cells are packed up into modules. Then you have different modules as part of racks, or sometimes referred to as strings as well. That's basically like one kind of sideboard of, a rack of different modules. And these are then often put into containers. It's what you see, that these white boxes, shipping containers, kind of packs or banks, different names. And there's the enclosure. Depending on the architecture, you get the PCS on the string level or multiple strings connected with one PCS or inverter. And then that's going to the medium voltage transformers and then the high voltage transformers that ultimately connect it to the grid, if we're talking grid scale batteries.
Great. I love talking about all this technical stuff and how it works. And one thing that was very interesting that you were talking about is how if you have a cell that doesn't perform as well as the other cells, and are you monitoring things on the cell level? Are you changing the way that cells are charged and the way that they're dispatched? And what kind of level do you do that on?
Yeah, that's a very good question. And the topic of having a good data strategy is phenomenally important. Reason being, I mean, batteries are fully digital systems, so they generate a lot of data. And generating a lot of data means it also becomes pricey to collect that data and bring it into the cloud. So you need to find a good balance of what is enough data to get meaningful insights that you do need, because ultimately you have $100 million, $1 billion worth in batteries sitting on a field there that you need to operate and optimize in order to make your return over the 20 years period that you operate the storage without any fires, without any major downtime. In Texas, for example, it's very few days that you actually make the revenue. So for these days, you definitely need that availability. But to collect all the data, you're just paying too much. So it's that striking that balance. And then what we are using and what seems to become more of the industry standard is that you do collect the data on string or rack level. So it means you don't have actually the cell or module data, but the average for the string, and then the min max values for each cell. So the highest cell and the lowest cell, to get an indication and read on the spreads within the strings. And from there, you can get meaningful insights on the current status of the system and the currently available energy from each of these strings. And then it, of course, kind of adds up towards the overall site level, which then includes the limitations of different PCS components as well. And from our perspective, to analyze all of that, we also like to have the ancillary components like an HVAC system to understand how well is kind of the overall system operating and what kind of temperature gradient can we expect. Now, coming back to your original question on how we help in that, is we do not touch and control the storage. And you wouldn't want us to do that either, because that becomes, from cybersecurity perspective, obviously a critical element. And you want the storage to be operated in the way that it has been designed from a controls perspective. So what we feed in there is we give the safe operating envelope in which you can operate without any power derating or without running out of energy. And we give a clear instruction for the maintenance teams on how to bring the storage capacity back up to its fullest potential by, and that could be, for example, turning off certain racks. So that's an interesting case that we had with some customers where, because these strings are all put in series, the weakest element ultimately limits the overall available energy. So if you have one string that sits at, say, 50% SOC, state of charge, and one that sits at 70% state of charge, and then you equally charge these up, the moment the first string reaches 100%, the others stop charging as well. So you have this amount of stranded energy. In this case, there was a 70%, so it's 20% differential, and that cannot be used. Now, if that's big enough, it can be beneficial to just turn off one rack, in particular if a faulty component is causing this, and wait for the next maintenance team to come in. And that might actually unlock more capacity than just operating the entire storage.
So when a battery goes bad, you will notice that and then notify somebody. Is that also what will happen?
Yeah, absolutely. So, I mean, behind this lies really an in-depth understanding of how cells and batteries behave. And it's about understanding which cells are kind of what we consider a weak cell. So ultimately something that has already degraded heavily or is a manufacturing defect. So you want to replace them. And if we're looking at a storage, we generally differentiate between what is lost or degraded energy. So this is the regular degradation that everyone sees on battery cells. I mean, everyone is familiar with their phones. You just lose capacity and there is a resistance increase on these batteries. That's gone. You can't really do anything about it. But the reason, and there was a famous study by Moto Energy recently where they said a BESS loses 8% capacity per year. When they said that, what they meant was the available energy at the point of interconnection was 8% lower the second year than the first year. Now, a lot of these 8% is likely not coming from degradation, but it's coming from what we refer to as recoverable energy. Some people call it stranded energy. This is stranded because of imbalances in the system, because of recalibration issues with SOC readings being wrong. So the state of charge, and we can talk about this a little more as well, is a critical topic, of course, to know how much can you discharge and charge. Now, with an LFP cell chemistry, the open circuit voltage, OCV, is very flat, which means if you base your SOC off a voltage reading, it's extremely hard to do in the medium window SOC. So say 10 to 90% or 20 to 80%, it's very hard to actually get any kind of voltage change. So just using that is...
And that's for the LFP battery. So that stands for lithium ferrous or lithium iron phosphate. And that's the typical type of lithium ion battery that people use in energy storage systems today.
Correct. I think by now almost all the systems that are being put on the grid are LFP chemistry, very reliable, very safer than NMC for sure, very safe.
And so what you're saying is like it's hard to use voltage to tell if the battery is fully charged or not because it's very flat instead of going up and down. Whereas like with other types of batteries, maybe like a lead acid battery, you could tell more about how dead it is compared to what the voltage is. So other things that you would do maybe is what they call Coulomb counting. And a Coulomb is a whole bunch of electrons, and they can count, what state of charge it is, also not by just telling what the voltage is, but how much current went into the battery for a certain amount of time.
Absolutely correct. And that introduces errors over time. So if you just recalibrate it, you might be fine. But if you then only rely on Coulomb counting, at some point you'll introduce an error. And that can be quite big. So we see LFP systems sometimes with up to 15%, 20% SOC error, which is massive not to know this. And it obviously adds up with imbalances adding on top of that. And if you fully charge it, actually, I mean, you said that, then you probably know, because at the high end of the SOC range and at the low end of the SOC range, the OCV actually does change. So you do see that voltage going up. And by that point, an SOC algorithm can recalibrate. Now, with these big systems, it's sometimes difficult to get all the cells into that window, and you don't naturally get that necessarily if you run on, say, ancillary services or frequency control, where it's more on the kind of mid SOC ranges. So getting this right is, of course, extremely important. That's where we help. And I lost track on what I tried to tell. But
so I've always wondered too about, one of the things about a battery is if you charge it 100% to 0% every day, it'll work. In the short term, it could be a good thing because you get more out of it in the short term, but then your battery doesn't last as long. And there's always doing software updates, and this could be for battery energy storage systems or cars and things like that. And so what's to stop a battery company from at the end of the warranty saying like, okay, now we're going to just not care and go from 100 to 0%, or even start doing that a month before the warranty expires because it'll take a little bit longer than that. How do you trust people about that kind of stuff? And a lot of times people can't see what's happening inside. I guess for a large energy storage system, you'd be more likely to kind of take a look at the data. What do you think about all of that?
So, I mean, what you're referring to is the combination of cyclic aging, meaning the full cycles of a battery, versus the calendaric aging, the more natural degradation of a battery that happens from just being there. Mm-hmm. Now, as you said it, in a BESS, in a grid scale battery, it's very closely monitored. And the warranty conditions actually are very specifically about the equivalent full cycles and the duration and the energy throughput. And I'm saying very specifically, they're almost always slightly different, and it's extremely difficult to calculate that at times. Sometimes it's easier, sometimes more complicated. They provide a very, very clear temperature window as well. So even if you're exceeding that temperature window, that will have an impact on how much is actually warranted. Now, if you're looking more into the consumer or automotive space, I mean, in the automotive space, it's, I think, famously kind of translated into miles and age. So you would get, I don't know, 160,000 miles on a car, or 100,000 miles on a car warranty for the battery, or 8 years, which is kind of giving that introduction of, you have a calendaric aging, which is the 8 years warranty for 70% of the battery versus the 100,000 miles on the cycling. And then, of course, I mean, in the car industry, also this element is, yes, if you quick charge every day, it's going to impact the degradation heavier, but the car OEMs at least have shied away from pushing that onto the plate of the customer and said, well, you don't worry about this, we'll warrant it no matter what happens. Mm-hmm. So they have to kind of assume the worst case scenario. Whereas in the BESS industry, it's often very strictly defined in what a customer can actually do. And that's usually based on the use case that they're intending to operate the battery in. Having said that as well, a BESS is used with a lot less power. So the C rates are lower than they would be in the car industry. So when you have high power charging, you often charge at 4 or 5 times the maximum capacity. So you run kind of 4C or more, whereas most BESS 4 hour.
So that would mean you could charge your car 4 or 5 times in an hour.
No, I mean, basically you have a
4C rate,
50 kilowatt hour battery, and you want to fully charge that in 10 minutes. So you have like a 250 kilowatt charge, say. So
okay. Yep.
Then so the amount of energy going through it versus the capacity is quite high. Whereas a BESS is discharged at often so 4 hour battery would be 0.25 C. So you have, say, 100 megawatt hour storage that is discharging at 25 megawatt. So the battery is less stressed from that discharge. So it's something that has a lower impact on degradation of the batteries.
We interrupt you for a very important announcement. Shaun White's Solar and Energy Storage Podcast has been brought to you by Shaun White's Solar and Energy Storage Podcast. That's right, Shaun White is sponsoring his own podcast, and he wants to remind you to go check out some of his classes. You can go to SolarSEAN, that's SolarSEAN.com, and then click on the links to check out his classes. You can check out his heat spring classes, and you can also hire him to teach classes for you, like at your company, something like that. Now back to the show. Yeah, I like to explain the C rate as how many times you could discharge something in an hour. So if you had a 2C rate, that means you could discharge your battery, or maybe charge it twice in an hour. So it would be like a half hour to fully discharge. And if it was a 0.5 C rate, that means it would be 2 hours before you could charge or discharge it. I think they go by discharge, but it's kind of the same thing. Yeah.
0.25 would be 4 hours.
Yeah, and 0.25, 4 hours, 0.5, 2 hours. Yep.
Yeah, exactly.
So another thing that I've always wondered about is who gets to decide what 100% state of charge or 0% state of charge is? Can you decide that?
That is a brilliant question. And we had this topic of what is actually the denominator so many times. So the easy answer for BESS is, well, it's the point of interconnection, right? You have a rated power that you need to be able to give to the grid. And that is after all the round trip efficiencies or losses that you get. So if it's 25 megawatt for 4 hours, then that's the 100%. Now you have ramp phases, you have round trip efficiency losses. So the actual capacity has to be higher. With a 5% round trip efficiency loss, you might look at 105 megawatt hours already that you need minimum in order to fulfill that. And you need to add on top of that safety margins for any imbalances that are building up or any inefficiencies in the system. So you very quickly end up with what we call an overbuild. So the equipment capacity is oftentimes 10 to 15% higher than what you get at the nameplate, meaning at the point of interconnection. And then you also get kind of installed overbuild as well. So when you buy a module, say from CATL or any other vendor, LG, you name them, they give you a rated power and energy for that module. And in order to make sure that they fulfill the warranty, they also add a marginal overbuild. So the entire install capacity is even larger than the equipment capacity, which is larger than the nameplate capacity. And that where that is measured is another point, is that the DC capacity, which a lot of companies do, is it at the transformer level, at the point of interconnection. So at what point do you actually measure this? And that, of course, matters for you as an owner operator, because you might kind of, as a good practice, you want as much back-to-back warranties as you can. So you're selling your energy, say, as a part of a power purchase agreement, a PPA, to an off-taker. And ideally, you want your battery supplier to meet the exact contractual obligations that you hold so that you don't run any risks. But oftentimes, you only get that warranty at the DC level. So they only guarantee that you get this energy to the DC inverter, and whatever you do with the transformers afterwards, which might induce more losses, is your problem.
Sure.
Or the problem of that warranty and that contract you have with that supplier.
Yeah, and another thing that I've kind of wondered about too is, like, you get a battery brand new, energy storage system, battery cells, all that. It's going to have more capacity, be able to hold more than a year later, 10 years later. And so a lot of people say, like, oh, I'm going to run these batteries between 80 and 20%, or maybe with lithium iron phosphate, maybe they're running it from, up to 100%. But who gets to decide what that means? And a lot of times it's just the battery manufacturer, and they're doing software updates. And batteries are kind of special too. They're just chemicals moving around, and they might sell you something and then have a lot better information 10 years later, and they'll change the charging algorithm and the different set points and things like that. And then I kind of worry too sometimes, is like, once the warranty is over, are they going to have an incentive to do something where, like, oh, we don't care as much, we actually make more money if this battery fails now?
So let's dissect this. So, I mean, absolutely, the degradation happens. And that's why you have an initial overbuild, and you limit the depth of discharge at the beginning to what you suggested, 20 to 80%. But that really depends on how much of an overbuild you have, which was also depending on how is the overall contract structure. Are you thinking about augmentations, meaning adding more capacity in time, new modules into existing containers, or rearranging these modules depending on their capacity and then adding a new container somewhere with additional power, or just doing a complete AC augmentation? So that is the plan on how do you keep enough capacity available for the entire period. And then what happens afterwards? Are we just going to run it into the ground in a merchant operation by just selling whatever is available? Now, the contracts with the supplier really determine a lot of that. Sometimes they mandate you to use only a certain window, but then you're free to operate within that window. Sometimes the operating profiles are very narrowly defined for that contract period. Now, generally, for almost, American vendors sometimes did that to push over the cloud updates, over the air updates, to change the way these operate. I think most owners operators really prevent companies from just doing that and require a quality check and a review of what that software update actually is before allowing it, just for the pure sense as well that something could go wrong and take the storage offline, which could cost a lot of money. So ultimately, there's a degree of control to what kind of software updates are pushed. But yeah, you're right, of course. I mean, if you change the control architecture or the way that the controls work, you could potentially influence the way that a battery is degrading. Now, the malintent that you kind of alluded to at the end of a year, at the end of
I'm trying to make up some conspiracy theories. Yeah,
yeah,
sure.
well,
Yeah.
20 years to just ruin the batteries.
Uh-huh.
I don't think that's necessarily true. But what we have seen is where integrators convinced an owner operator to augment, i.e., buy new batteries a lot earlier than that was necessary because their original design actually didn't work. And they claimed that was due to degradation and a new augmentation is necessary in order to meet their nameplate, which ultimately costs the owners more money. There was kind of an imprecision in the contracts, I would say. But it's alluding to what you said. They appreciated making more money earlier versus ensuring that the existing infrastructure is maintained well.
Great. Okay. Well, let's see. Is there any other things that you wanted to cover or talk more about your company or let people know good ways to do business with you?
Yeah, I mean, the exciting part is that with batteries, we see a technology that is so incredibly powerful in helping stabilizing the American grid and making it ready for scaling as well, especially with data centers coming on the grid now. And the amount of data that is coming off these battery storages is so phenomenal that it's very tempting also to try something in your own engineering teams. And a lot of companies do that and then can only really encourage that kind of to get to know the technology and to take more responsibility. But especially once you think about scaling, you have different integrators, you have different OEMs, different cell chemistries, different form factors, different kind of architectures on the side. It becomes extremely difficult to manage all these different data streams and to have someone helping you to normalize the data, to create clear and comparable insights and give clear recommendations on how to ensure safe and performing battery operation. I think it's going to become crucial if anyone is thinking about scaling their best business.
Great, great. Okay. Well, make sure everyone to contact Lennart Hinrichs and figure out how to get your battery systems optimized and get all the data and work with AI. That sounds really exciting. Let's see. Anything else like where people can find you?
Absolutely. Yeah, I mean, check out our website on www.twaice.com and reach out if you have any additional questions.
And we'll put that in the show notes. And where are you located?
I'm in Chicago.
And do you go to the solar conferences around the country, such as do you go to RE Plus?
Absolutely. So RE Plus, of course, is the big one. We also have regular presences with the Informa Markets shows surrounding the EES event and the
Okay.
Battery Asset Management Summit. There's a bunch of
Great.
these that are conferences that are scattered around
How
the
about do you go to the Smarter E conference? You know that one?
The Smart Conference is I'll be in San Diego in February.
Oh, Intersolar in San Diego, and then
And then the Smarter E in Munich is our main show every
yeah,
year. Of course, being a home match, TWAICE originally is a Munich-based company.
great,
So
great. Yeah, and so the Smarter E is also known as Intersolar, and they have the biggest conference in Europe. Perhaps it's the second biggest conference in the world after SNEC. I don't know. I'm just taking a guess.
it is definitely bigger than RE Plus.
Yeah, and I love going to that conference too, and I'm on an award jury committee. And so I'll see you at one of these conferences, Lennart.
Yeah, looking forward to that, Sean. Would be
Okay.
And by the way, we do have what we call a battery encyclopedia on our website, which is like a glossary of the most important terms in the
Oh,
battery
great.
space. So if you want to point your people there to
Okay.
learn more about acronyms, that might also be valuable.
Okay, so everybody go to the Battery Encyclopedia over at the TWAICE website, and that's spelled TWAICE. TWAICE. Check that website out twice. All right, well, thanks everybody for listening to this podcast. And I want to just remind people too, if you want to understand a lot of these different acronyms, SOC, BESS, what you can do is take one of my classes and get yourself NABCEP certified, like for the ESIP. That's another one. They can call it an acronym like an ESIP, and that stands for the Energy Storage Installation Professional Certification. And that way you will be acronym and abbreviation smart, just like Lennart Hinrichs. And thanks for listening to Shaun White's Solar and Energy Storage Podcast. To find out more, go to SolarSEAN.com. Woo!